Hi everyone and welcome to this new video. Today we're diving into luminance, chrominance and the saturation node. If you've ever wondered about the different luminance math options, you're in the right place. This will be a fairly theoretical video with some arithmetic along the way, so I hope you're feeling ready after the Christmas festivities. So, without further ado, let's get started. So, what is luminance? Well, before discussing this concept and see that in Nuke, I thought to sketch some process here, just to recap all the steps that are involved. It's helping me to visualize things from left to right, and I'm gonna be very quick. Okay, so I hope to not bore you. So it basically starts with a light source. Okay, we have our sun, and our sun we can imagine it as a sphere in some place in space. And thanks to all the nuclear explosions that are happening on its surface, the sun is shooting out energy. It's shooting out electromagnetic energy that is moving through space, and we can imagine these light rays as a bunch of waves literally moving in a certain direction. Okay. Now I just draw this one, but it's in every possible direction, right? So this energy, this electromagnetic energy, is moving through space, and we can imagine it as waves going up and down till they reach something. Okay, if there is nothing to reach, well, they will keep going forever. But if there is some sort of material, if there is some sort of object in between our light source and our acquisition system, well, here it's where the interesting part happens. So this wave will be reflected by this object and will then interact with some sort of acquisition system. In this case, I just draw this little eye here. Now, before seeing this part, let's zoom a little bit on this poorly drawn wave. So an important concept when we are discussing colors and why they are different and why we perceive certain color and stuff like that. An important concept to describe is the concept of wavelength. So basically, we can draw this little line from the peak of, we call it, wave A and wave B, right? So this distance is basically what's called wavelength, right? And wavelength is somehow related to the energy, the amount of energy that each package has from its source, right? So the shorter this distance, the higher the energy, the wider the distance, the lower the energy. And we need to introduce another concept that is frequency. So if we pick a unit of time, okay, this is a unit of time, and we count how many waves will move through space in this amount of time. Obviously, if the distance from one wave to the next one is big, well, we're gonna count less waves in this amount of time, right? Because obviously there is so like a large distance that there won't be many waves moving through space in this short amount of time, right? If instead the distance from each peak is very little, so if we consider this type of wave, well, here we have a very short distance from point A to point B, meaning that we're going to count many waves in the same amount of time. Okay, that's in a very simplified form, that's the concept of frequency. Now, it makes sense now that we see this that the higher the distance between each wave, the lower the frequency, right? Whereas the lower the distance between each wave, the higher the frequency. And the lower or higher frequency is proportional to the amount of energy that each package of waves is basically carrying. Okay, now here it's completely random, but again, this should clarify this concept. Okay, if we consider electromagnetic energy as a bunch of waves moving through space, well, the larger the distance between one wave and the next one, it also means less energy, because the frequency, meaning the amount of wave that will basically move through space in a certain amount of time, is going to be lower. Less waves means less energy. Instead, if the distance between two waves is going to be shorter, it means that we're going to count more waves in the same amount of time, and more waves means more energy. Okay, this is a concept that is going to be relevant when we're going to see this. Okay, the visible spectrum, and the frequency is going to be an important concept here. So the question now is, where on earth are the colors and the luminance? I mean, okay, we have understood that the sun, is emitting energy in the form of electromagnetic waves, and then, these waves can be closer together or farther apart. The concept of frequency that we discussed before. But what are the colors that we see? I mean, do they travel as waves through space or not? Actually, no. Colors are not directly contained in the electromagnetic waves. Instead, they are an interpretation that our brain creates based on the different frequencies that reach our eyes. In other words, the electromagnetic radiation propagation through space is not colors. It's just energy at different frequencies. This radiation then interacts with various surfaces. We have this tree, this apple, this, I guess it's a blueberry. And, each surface is made of different materials and therefore different molecular structures. Based on these physical properties of each material, some of the incident frequencies will be absorbed and won't reach our eyes or our camera, while other frequencies will be reflected and then they will reach us, our eyes. These frequencies are then captured by photoreceptor and translated by our brain into meaningful content that are actually the colors. Now, the frequencies that reach our eye are captured by two types of photoreceptors. Essentially, you can imagine that there are like photosensitive cells in our eyes located in the retina that are stimulated by the frequencies of electromagnetic radiation. Like these two types of cells gather various pieces of information that through a complex network of biochemical processes are interpreted by our brain to provide us with a representation of what we're actually observing. Now, some of these cells are more sensitive to variation in the frequencies of the reflective radiation, meaning this, and are therefore capable of transducing signals that will be interpreted as colors. It has been shown that these photoreceptors are like extremely sensitive to three specific wavelengths, which correspond to the color of red, green, and blue. And let's say that the perception of all the other color is in fact based on the combination of these three primary frequencies. However, there is a second category of photoreceptor that are more sensitive to variation in the intensity of the signal. In other words, these photosensitive cells are more attuned to the brightness of light rather than the color itself. And this is where the concept of luminance comes in. Luminance refers to the amount of light perceived by our eyes and related to how light or dark a particular color appears to be. All right, so let's do a quick experiment here. Here we have three color circles corresponding to red, green, and blue. And if we check the intensity of the three colors, meaning the code values for each color channel, since we are in Nuke, we immediately notice that the values for red, for green, and for blue are the same. 1, 1, 1, right? So if I sample here, 1 in the red, 0 and 0 in green and blue. If I sample the green, we have 1 in the green, 0 in the red, 0 in the blue. And if I sample the blue, we have 1 in the blue, 0 in the red, and 0 in the green. So it is as if we're saying that the intensity of the electromagnetic signal inducing the perception of red, green, and blue is exactly the same for the 3 circles. So imagining that we could turn off our photoreceptors sensitive to color variation and leave only those sensitive to signal intensity active, we would expect to see 3 circles of equal intensity, right? Actually, that's not the case. The human eye is more sensitive to the green light than it is to red and blue. And that's why we see the green circle brighter than the other 2, right? So the intensity of the color, meaning the quantity of color in the red, green, and blue is exactly the same. If we translate this to the concept of electromagnetic waves, it's like the intensity of the signal for the red, the green, and the blue is the same, yet our eye is perceiving the green brighter than red and blue. Okay? So for some evolutionary reason, our eyes tend to perceive frequencies of light in the green as brighter compared to those in the red and blue ranges, even if the signal intensity is the same. Interesting, isn't it? So if we wanted to convert an image into its luminance equivalent, meaning if we wanted to view an image solely through our photosensor sensitive to light intensity and not to color, we couldn't just take an average of the color making up the image. Instead, we would need to account for how our eyes respond to the different frequencies present in the image. And this explains the reason for the presence of different formulas within the saturation node. I mean, different formulas for calculating luminance. So let me grab a new saturation node and I plug it here, right? Now, by default, the luminance math that we see in here is Rec 709, but we have, different formulas, and we're gonna see them in a minute. Basically, when we desaturate an image, it's as if we're turning off our photoreceptor sensitive to color and viewing the image in grayscale, right? So it's like turning off the color and viewing the image just in grayscale, basically from black to white. And by default, the luminance math in the saturation node is set to Rec 709 because this is a standard that approximates very well the luminous efficiency function of our eyes. In other words, the way that our eye responds to the intensity of light signals at different frequency within the visible spectrum, right? So it basically approximates the way our eyes works compared to the different color and different frequencies of light that reach our retina. Now, in practice, the Rec 709 provides a conversion of color to their corresponding luminance by matching the sensitivity of our eyes to various colors. Okay, that's what it does. Now, the formula that we use in here, so whenever you set your luminance math to Rec 709, the formula that you're using is actually this one here. Okay, so this is actually the same math that Nuke is using when you see the luminance value in here. Okay, so if I sample my color, let's go back to, let me turn off the saturation node. And you see that when I sample the color here, we can read the corresponding luminance value in here, right? And the math that is used is exactly the same, right? So this formula is the way that Nukes give us the luminance value when we are sampling a color, when we are sampling pixels in our image. And it's the same formula used by the saturation node when we are desaturating using the Rec 709 standard. Okay, it's the same math, and now we're doing some example. So let's grab a more interesting picture than this tree circle, maybe here. Okay, I have this actress staring at us, and let me, well, okay, I wanted to delete this, but we're gonna see those nodes in a second. So we have this actress here. Maybe for clarity, I'm gonna move these nodes in an empty region, so it's more easy to follow. And let's sample some pixel, and let's see if this formula is actually working. You know, I'm expecting to, you know, sample some pixel, maybe 1 pixel for now. Okay, so I'm sampling this pixel here. I read the code value for the 3 different color channel, and I have a corresponding luminance value here. I'm expecting to get the same number by doing myself, you know, the calculation, by doing the math myself. Okay, that's what we are trying to do here. So let's start by creating, just for clarity, a sticky note. Okay, so I want to just type down our red, and our red is 0.53328. Okay, I'm reading down here. Okay, then I'm gonna read my green. All right, and my green is 0.36131. All right, and then I have my blue, that is 0.27050. Okay, so these are the value that we are reading from this pixel. Okay, and if we switch between the different color channel, oops, let me move my mouse in the viewer. If we switch between the different color channel, we can see the red, the green, and the blue. Okay, so obviously the red, even by eye, without checking the actual number, we can see that it's the brightest, meaning that it has bigger values compared to the other 2 color channel, right? So even without checking the number, I can have a clue that the let's say the highest or the biggest component that makes up this pixel is actually the red. And it makes sense, we are sampling our pixel from her skin, so it makes sense that it's the red, the more present. But why are we getting this number? Well, this formula is actually explaining why. Okay, so let's do some calculation now. Let me grab my calculator. All right, and so let's do some math. We need to basically scale our current red value by this scalar. Okay, this is basically a weighted sum of the 3 different color channels, and I need to multiply my red by this value here to get, you know, the new red, let's say, that is going to be summed with the new value for the green, the new value for the blue, and all summed together, they're going to give me the actual luminance. Okay, so let's try to do that. I'm going to grab my red, I'm copying it, I paste it here. All right, so okay, and I multiply this by 0.2126. Okay, and this is my basically new red. Okay, it's the new weighted value for the red channel. Okay, so there you go. Then let's do the same for the green and the blue. Okay, so I'm gonna copy my green. All right, and I'm gonna paste my green, and I'm gonna multiply my green by this value 0.71520. 0.71520. All right, this is the final number. Let's copy this. So this is our new weighted green, let's say. And same thing for the blue. So let's copy our blue. And let's paste it here, and we're multiplying it by 0.0722. 0.0722. Okay, this is our weighted blue, right? Let's paste it here. Blue. And there we go. So these are the current value that we read in red, green, and blue. And these are the value after we weighted them using a specific scalar for each color channel. Okay. Now, in order to get our luminance, we need to sum all these three together. And we are expecting to get this number, right? So let's do it. I'm gonna clear this, and I'm gonna do one. I'm gonna copy this, and I'm gonna paste it here. And we want to sum this with this. All right. So I want to sum it with this number here, and I want to sum this with the blue, right? So let's copy. I want to sum this with my blue, and this is gonna be the result, and there you have it. Okay, there is some difference in, you know, the very last digits, but you know, 0.39131130. That's okay. You know, we don't go that far in the digits. Just to prove you that the formula is working. It's exactly what Nuke is doing under the hood to provide you this type of information, right? Now, if we are desaturating this using the Rec 709 math inside within the saturation node, let's see what happens. So I'm gonna create a saturation node, right? Plug it there, and I'm gonna leave my luminance math to Rec 709 and desaturate my image. Now, if I sample this pixel, look what happened. We have the luminance in all three channels, right? We have the value that we were viewing here, right? When we are sampling this pixel, here we read the three different values for red, green, and blue, and here we have the result of the weighted sum based on the luminance equation within the Rec 709 standard. If we apply the same standard within the saturation node, this number will be basically copied here, here, and there, right? In all three channels. And there you go. Okay. The same math is applied for all three channels, of course. And, you know, the luminance value is then basically presented in the color channel. Okay, it's like we are copying the luminance within the three color channel, so the same value for the three color channel, and showing this image in grayscale, right? So this is proving that basically this formula is doing exactly the same within the saturation node and, you know, in the viewer, meaning that under the hood, Nuke is doing the same math to show us this value here. Okay, so let's return now to the initial example of the three color circle. Let me frame them here and also clear this out, because I would like to explore the other formulas available in the luminance math tab of the saturation node. So the second option after the Rec 709 is the CCIR 601, now formerly known as ITU-R BT601, in short BT601. This is a standard for video encoding, and it's based on a slightly different weighted sum compared to the Rec 709. Okay, so this formula here, this way of calculating luminance, is based on a similar approach compared to the Rec 709, but we are using different values, right? So we're basically giving more weight to the red and less to the green compared to Rec 709. And the reason is that this standard was optimized for SDTV, so standard display, pretty much. whereas the Rec 709 was developed for HD TV. So two formulas that are doing the same thing, but for different type of devices. So they differ, they are different because they are optimized for the specific devices that they were developed for. The third option is the average. So let me open up the saturation node set to average in the Luminance math. So it's the third option. And what it does, it simply calculates the mean of the three color channels, right? So if we view this three color circle through the saturation node set to average, you can see that we end up with three circles, with the same level of brightness, right? And that's because we are applying this math here. And you can prove it yourself by creating an expression node, and you can, plug it there. And now if we view it, we get the three color circle. So nothing changed. But if I apply this simple math here, okay, and I need to apply it to all three channels. There you go. I end up, having the same result. So these two are exactly the same. This is just to prove you that this is the math that is going on in your saturation node when you are setting it to average. Okay. Lastly, we have the max operation. So let me revert back to our color circle, and let me open the saturation with the luminance math set to maximum. And basically, this formula selects the color channel with the highest code value among the three and copies to the other two color channels. So it's basically creating a grayscale image where the value corresponds to the color channel with the highest code value. Now, it's maybe hard to see with this three color circle, because if I view it through the max, through the saturation node with luminance math set to maximum, we're getting these three white circles. So maybe let me create a fourth circle. Okay, so something like that. Maybe more central, and I want to output in RGB, but instead of being white, I want to have some value. And there we go. Okay, so now obviously the highest code value is in the red channel. Okay, so we have 0.54 in red. And if I'm plugging this saturation node where I'm, setting the saturation to 0 and the luminance math to maximum, and now I view the result, I'm expecting to get a black and white image, like a grayscale image with this value in all three channels. This is how the maximum operation is working. It's copying the highest code value in the three color channel, is copying the highest one into the other two to get the corresponding grayscale image. So let's try that. And there you go. So now we have this value copied in all three channel, and that's why we don't have color. So this is the way that the maximum operation is removing colors in the image, and what it's doing is actually copying the highest code value into the other two color channels. And that's all, folks. I hope this video has been helpful and that you've discovered something new. If you have any questions or comments, don't hesitate to write to me. Wish you happy holidays, and talk to you soon. Bye-bye.